Thank you very much. But I also want to say, even though Mickey so nicely told that we organized everything, I just have the pleasure to stand up here and talk to you about the topic that I absolutely love and adore. So it doesn't really feel like work. So it's a lot of fun, and I can only re-emphasize, if you love the topic up here, you can tell everyone about it. It's great. So I myself, I'm Sven. I'm originally from Switzerland, and I'm now here in Austin working at the astronomy department studying exoplanets. And more particularly, I'm studying the weather on exoplanets. So I'm going to tell you all about tonight why this is amazing, why we need doing that, and why this is one of the coolest research you will ever see in life. Yes. Let's get started. Very quickly, a short overview what I'm going to tell you. First, I want to make sure that we're all on the same page. So first, we're going to quickly talk about what is an exoplanet. What is that even? Then I'm going to explain to you how we discover them. Then the real part, the weather and the climate, and how we're actually simulating it. And then lastly, well, it wouldn't be an exoplanet talk if I would not address if we already found life or not. So if you want to get that out, well, you've got to wait until the end of the talk. I'll give you the top current answer of our research. Okay. With that, the first topic. What is an exoplanet? And the idea is rather straightforward. You do know our planets in our solar system. All 8.5 of them, depending on how you count. An exoplanet is all the other ones. So none of these. Not even Pluto. I'm very, very sorry. I know he didn't make the cut to be a planet. He also does not make the cut to be an exoplanet. It's a very sad story. I feel very terrible about it. But basically, whenever you go out into the night and you look at the night sky and you see all the stars in the night, exoplanets are planets just like ours that orbit those stars. And again, Texas is an amazing place to be for that because we have the McDonald Observatory out in West Texas, which has amazing telescopes to stare at the night sky and trying to find and characterize those planets. Which is also why the UT Astronomy Department is an amazing astronomy department in general that does great research because of stuff like that. So with that, this is what we've been doing. Like, this is what astronomers have been doing. We stared at the sky and we tried to find planets, and we've been rather successful. So we so far have found 6,000 exoplanets. So imagine that. Like, when I was born, 1995 was when the first exoplanet was discovered. We knew one. And now, some years later, I don't want to do the math, we are 6,000 exoplanets. And they have such a big diversity. From small to big, from gaseous to rocky, from hot to cold, we found so many different planets. And that is thanks to a lot of different instruments, a lot of different efforts, but especially I want to highlight here the Kepler survey, which is a mission dedicated to find exoplanets. And it basically just stared at one point in the sky for years, and it discovered thousands. Like, I think at least 2/3, probably more of the planets we know was just this one singular survey, which is incredible. This is now being followed up by others, like for example the Keops survey, which now, rather than staring at one spot for very, very long, it stares at the whole sky for very, very long, even longer, to really find those. Now, when we're talking about exoplanets, again, I already mentioned, there's a big diversity, but what are we talking about? There's many different categories of exoplanets. It's all like a fluid transition from one to the other. But I want to just go over like some of the typical planets we encountered. The first planet we found in 1995 was what we called a hot Jupiter. So this is a planet the size of Jupiter, the biggest planet we have in our solar system, and roughly as big as planets can get before they become stars. Was found at an orbit that is close to Mercury, so very, very, very close to their star. So that means because of the irradiation, they're very, very hot. So peculiar, like very peculiar planets that we do not have in our solar system. So right from the start, the first planet we discovered, we knew, okay, things are different out there. We really need to expand our horizon. Then from these Jupiter-sized planets, the next category are like Saturn, Neptune-sized planets. So they're still gaseous. There's basically just gas, a big blob of gas, but they're slightly smaller. But then it becomes interesting, because the next category that we're having are either, they have two names. They're called sub-Neptunes or super-Earths. That is because they're in between Earth and Neptune. So they're bigger than Earth, so that's why we call them super-Earths, bigger Earths. But they're also smaller than Neptune, so we call them sub-Neptunes, smaller than Neptune. And they're in between. They're very interesting because they have a rocky core, so just like Earth or Mars are rocky, but they have a mantle that is like a gas planet. Very peculiar again, very strange, something we do not have in our own solar system. And then the last category, and maybe the most interesting for at least everyone who wants to find an alien, are rocky planets. What you can see here is Earth, the prime example of a terrestrial rocky planet, but also Mercury, for example. Or I also put it up here. That's well, let me see. That's Europa. One of the moons that is actually thought to have life, might have life as well, because this is an ice crust and there's water underneath. We don't know yet if there's life. I can tell you that much. I'm not spoiling the end question. But it just shows you how diverse planets and moons can be. And we're not entirely sure yet what is all out there. One system that we know that we love is the TRAPPIST-1, because that has 6 terrestrial planets. And, well, let me get, those 3 here are in the habitable zone. That means there might be water on the planet. Or at least, if there's water, it can be liquid. And we think that is really, really important for life. So now that we have a big overview of like what kind of exoplanets are out there, let's go to the second topic. How do we discover them? I already mentioned a little bit Kepler and other stuff. But today I'm going to show you and explain to you the 2 main methods how we found exoplanets. The first is called the transit method, and that's right. It works very straightforward. We have a star, we have a planet. If the planet goes in front of the star is a little bit darker. It's exactly the same thing that happens, for example, during this lunar eclipse, where the moon goes in front of the sun, blocks it out. Just not that all of the light gets blocked out, but a little bit. And we actually have an example of that in our solar system, because a few years ago we had a Venus transit. So that is a real image, and that is the real Venus right there, blocking parts of the sunlight. Now if we go to further away planets, this is how our data actually looks like. So this is what we study when we study exoplanets. You can see here the light curve. This is how bright the star normally is, and if a planet is in front, it gets darker. Again, very straightforward, just like this. Now the second technique that we're using is called direct imaging. And it's exactly what it says. It's just taking a picture of the planet. So how do we do that? Well, let's imagine we have a solar system somewhere very far away. We have, in the middle, we have the star, then we have the planets around, and they orbit the star. Now if we take a picture, we of course don't see the orbits. They are invisible, like there's no line traced out where the planet is. They know where to go, they don't need any road signs. Now, the next problem that we're having is the star. While we do like stars, they're nice, they also cover up the planets. Imagine like someone with like a weak flashlight standing next to a lighthouse, and you're trying to see them, you probably don't see it, you just see the lighthouse. So we need to get rid of the star. So what we're doing is called coronagraphy, which is putting like a little mask in front of the star so that we don't see the light. And what we're hopefully left with is the planets. And what we see when we take a picture is this. I hope you're all excited. I don't know. I absolutely love this image because it gets even better. It gets even better. This is HR 8799 system, and we observed it for so long that we can do something really cool with it. We can actually see the planets move. That is so cool. This is real data. This is not an artistic expression. This is not an imagination of anyone. We took a telescope, we stared at the sky for long enough, and this is what we found. We see the planets orbiting. It's really cool. It's amazing, isn't it? Yes. Yeah. I love that we're all on the same page. Right. So now, I told you we found 6,000 of those, and I just want to quickly highlight again the diversity that we're having, which is called the exoplanet demographics. And here you can just see a little bit of like how they're spread out. So we're going from distance to the star to size here on this axis. And here we see exactly what I described before. We have the hot Jupiters, which are big and close. We have the super-Earths, which are kind of like in between the Earths and the gaseous planets. And we have something very exciting, nothing. This big hole nothing here is not because there is nothing, it is just because our instrumentation is not sensitive yet. We cannot find those planets. And that is what everyone is excited about. We want to have better telescopes, we want to have more time, we want to stare for longer to really fill that out and figure out, okay, what actually is going on here. So this is not a real, this hole is real, there's no planets there, they all died. But this is not real. There's actually probably a lot of planets that we have not discovered yet, and we need better telescopes, we need more time to find them. But that brings me finally to probably, well, at least in my opinion, the best topic of tonight, which is the weather on those planets. Because I personally love it. Well, everyone always says, like, yeah, we want to find aliens, we want to find life. I'm fascinated by the diversity of the weather on other planets. I love to figure out how just what is possible and how they look like. So what are we talking about when we say weather? Well, currently we are mainly interested at the climate. So here you can see an example of Earth, how it looks like. You can see the temperature. It is hot at the equator, where all the deserts and the other stuff is. And it gets colder to the top. Austin, of course, still in the hot region. Who would have thought? Oh wait, sorry, Austin here. Yeah, who would have thought? But this is what we call it when we talk about climate. It's like this big global maps of temperatures and winds and other stuff. So keep that image in mind. Because what I'm now going to talk about is Proxima Centauri b, which is cool. Because turns out the closest planet to our solar system, basically our next door neighbor, has a planet. And you can imagine if the closest star has a planet, this is a big favorite in the community, so there's a lot of effort going into modeling it. And how does the temperature of that planet look like? Well, something like this. Well, that looks different, doesn't it? Well, maybe a little bit, but it's like this big blob. The reason why this planet looks so different than Earth is because it is tidally locked. It is so close to the star that because of tidal forces, it always shows the same side of the planet to the star. It's the exact same thing as the moon. We always see the same side of the moon because the moon is tidally locked to us. And the same these planets do with their star. They're so close that they always show the same side. So they also get all the daylight, all the heat, all the radiation on the same side, which is here. So that's where all the heat is. And then through winds, which you can see here in the arrows, this gets circulated around the planet and heats the planet at other spots. But if you look at the temperature, which is science correct in Kelvin, but here where the white spot is where water freezes. So you can see those colors here, so the reddish colors are actually places where water might be liquid. And if you look at that, that is roughly the baseline. So this planet might be able to have liquid water in it. We don't know it yet, because again, our instrumentations are not good enough to really figure that out. But our theory tells us there should be something, or there could be something. And that is this is at least what I find very exciting. So quickly, so tidally locked planet, and there's maybe water. Very, very exciting. I know this is not maybe as pretty as like artists rendering, but this is real simulations, real climate simulations of other planets, which I absolutely love. Now, I showed you the demographics plot before. And you saw there's a bias towards big and close objects. That is because our observations are most sensitive. The bigger something is, the easier it is to spot, and the closer it is to the star, the better our chances of finding it. Very straightforward. That means hot Jupiters are one of the best objects to study, and ones where we can learn the most. So we did the same climate modeling that we did for this planet, we also did for hot Jupiters. And it looks kind of similar. So this is for HD 209458b, again, one of the first few planets that we discovered, and the first one that was at least reconfirmed with the transit method. So the one that I showed in the very beginning. The very first one we saw through the transit method. And we see the same kind of things again. We can see there's a hot spot, we can see the night is colder, and we see very strong winds. And I guess you can all already think about, that guy's probably tidally locked as well. And that's true, because again, it is so close, it always shows the same side to the star. Tidally locked. And because it is a gas planet, and because it is hot, well, what happens with hot air when you fix it? It rises, and it expands, it becomes bigger. So these planets have a big expanded atmosphere, which makes it very easy to learn more about. So those are one of the best studied objects that we have right now. Not necessarily because we want to study them the best, but because they are the easiest to observe and they allow us the most detailed insights. And the good thing is, physics is universal. What is true on this planet is true on another as well, so we can really use those to already learn more for others. Now, my personal topic that I like to study are clouds. I just quickly want to highlight that we also have on those hot Jupiters, we have very fascinating clouds. And they're made of this. Now, if you do love a lot of geology, if you have some geology nerds here, you might recognize some of them, and you already think like, wait, that's a bit strange. This is not water. This is not a liquid. Those are rocks. And that is because the temperatures are so hot that only really rocks can form clouds. So we have rock clouds on those planets. That's really cool. And that's not theory just being crazy. We actually have foundation. We do see those planets. We do see the rock clouds. And they can be made from manganese sulfide, enstatite, iron, or corundum are some examples, but there are several more. And you can see here some examples of what they might look like. Crazy cloud particle out there. I love it. Now this brings me to the last topic that I want to get a little bit closer, get you a little bit more information about. Are we alone? Well, I quickly want to ask, who of you believes there's aliens out there? Please give me a show of hands. That's really cool. Me too. By the way, answer. I definitely believe they're out there. Who of you believes we already found at least evidence of life out there? I love it. You're all very optimistic, but unfortunately, you're slightly wrong. While there's maybe some people who have a little bit claims, the true and real answer for the current state of our research is we don't know. We really don't know. We can neither confirm that we found life anywhere, nor can we say that it cannot exist. It's really in between those two things. And we're trying our best, I tell you. We're really, really trying, but it's very difficult. And I just quickly want to highlight two main things how we look for life. And the two things that are currently being researched is either we're looking for biomarkers, I will explain in a second what that means, or we're looking for intelligent life. Now the Intelligent Life Survey, you might know this is called the SETI, the Survey for Extraterrestrial Intelligence. And that is very particular because this assumes that life not just exists, but it is intelligent and it has similar technology than we have, or at least the technology that we can recognize. While the good thing is, if there is intelligent life, it's very easy to find because typically, like, we have a big footprint, we send out a lot of signals into space, so they might be recognized, but also the chances of by chance finding intelligent life is way more difficult than finding non-intelligent life. So while this is active research going on, I would say most efforts are currently for biomarkers. And biomarkers is also, the idea is very straightforward. If you look at, this is a spectrum, it's basically just the different colors of light. And we have Venus, Earth, and Mars. And you can see, if you look at the spectrum of those planets, at the different colors they emit, we can see they have a signature here of CO2, Mars has it as well, but Earth, who is life, has way more complicated signatures. Now, for example here, water. Now if you look at an exoplanet, it looks something like this. Again, a spectrum, some wiggles, and we can now figure out, oh, those wiggles are water. Exciting, we found life. Nah, not quite. The thing is, this is from a hot Jupiter again. So this is water vapor. This is really not that helpful for life. If you ever burned yourself with water vapor, you don't want to live there. And so it doesn't really any other life. So it's not that straightforward. And there's a second problem. While on Earth, maybe like our oxygen is produced biotically, it doesn't necessarily have to be that way. So this is just some examples of like different environments. This is Earth here, but we have a lot of other options of how we can get oxygen into the atmosphere. And so we cannot really say like, oh, we found oxygen, we found life. That's way too simplistic. Or, oh, we found methane, we found life. Also way too simplistic. But where it gets a little bit better is, what if we find oxygen and methane? Because we know that those two, they like each other a little bit too much. So if you have oxygen and methane in the same atmosphere, they want to react. They want to get together. There's nothing much that can So the only way how you can have both in an atmosphere is to continuously produce them. And the only way we know so far is through life. But again, so far. There's a lot of aspects of that. Before I end, I want to quickly show you one exciting picture from the solar system. This is again Europa, this is Enceladus. And those two, I already said, they have water underneath. And then Enceladus, you can actually see the water escaping through some balloons. So this is within our own solar system. And the question is currently, because there's water, because we know that there's carbon and complex molecules in there, technically, life could form there. So we are currently very excited to try to go there and see if there's actually may or may not be life. But again, we are excited, we want to find out, but so far we don't know. So to give you a quick summary, I showed you that exoplanets are diverse. I showed you how we find them. I think we already found over 6,000 of them. I convinced you that studying their weather is the best thing anyone can ever do. And we talked about that we're still looking for life. And we've not given up yet. We're trying really hard, but it is difficult. So yeah, I'm very happy to take any of your questions. Thank you so much.
Who has the first question?
Thank you. Okay, so I'm curious. So going from the solar occlusion model, how do you guys get the actual weather patterns? Is that a projection, or are you guys using more sophisticated techniques to actually see the direction of where these heat flows are going, that kind of thing?
That's a great question. So we are actually using Earth weather forecast models. So that is where a lot of the idea is based on. Now, when I say we're using Earth weather forecast models, it's again, a little asterisk. We had to adapt them a lot because those planets are nothing like Earth. But the cool thing is, and that holds true throughout all of the physics, probably also for the other speakers that we're going to see tonight, physics is generalizable. So if the physics is true here, it is true on another planet. So if our model works here, it has to work on another planet, plus minus some differences between the planets. But we can model them. And the cool thing is, right now we're still trying to figure out, but whenever we made a prediction, we were actually surprisingly close to the truth. So we were never spot on, but we got we got the gist right. And that is, basically we need those models to figure out more and more because our observations are limited to those little wiggles. And to really get the climate, we need the theoretical models.
Hello. Are you afraid of for the search for intelligent life that maybe there's hostile intelligent life out there and the consequences?
That's a very good question. And I first want to give the overarching science community answer is yes, we're thinking about it. There's groups that actively study how should we approach it, how should we do it. So yes, this is definitely a concern of people. But you asked if I am worried. So you asked specifically me. So I can give you my answer. If that is no, I'm not really worried. Because space is big, space is difficult, and just figuring out how to travel through space, it sounds like we're nearly there, but we're nowhere near close. And even once you can travel through space, there's so many difficult for this galaxy-wide civilization that they barely cannot function. So if there is intelligent life out there, I think the worst case is a very boring email response with them. And I'm not too afraid of that. I don't think there's a chance of coming here. But that's again me. There's other people who think more differently about that.
Yeah, I mean, crossing the ocean was really difficult too, and the people who figured that out first, not so nice.
I would say space is a little bit bigger than an ocean, so we have maybe a little bit of time.
It's really,
at least not in our life. We don't have to be worried. I can guarantee you that.
What do you feel like is the best planet in the solar system for prospects for actually confirming biological life on it? We could actually go and sample it, because with all the things you're talking about, it's kind of it seems like decent odds this thing could have life, but for a lot of people it would have to be we actually saw it, a probe went down there, sampled it. It's like, what's the best prospect we have for that?
It's the last section, Europa and Enceladus. They are basically, there can be life. Like, it's not like Mars, where people are like, oh, there might have been life, or if life could adapt, then maybe. No, Enceladus and Europa, they could have life like ours. There's nothing stopping it. So the only reason why there wouldn't be life is if it hasn't evolved. That's the only reason. Which is, like, the bar is as low as you can put it. Like, it doesn't get any better than that.
It's interesting to me how much in astronomy you can make deductions based effectively on measurements of light. And when I think about something like nuclear physics and how fine-tuned measurements of mass and magnetism and all sorts of things you're able to do, it's hard time for me to square that you think you have so much understanding about everything based on this kind of crude measurement methodology. And I'm just, how would you respond to that sort of thing as an astronomer?
Yeah, so that is, I think that's a very, very valid criticism, and I would love if we had another option, but we don't. The only thing that reaches us from those distant stuff is light and gravity, but gravity doesn't help you with exoplanets. So I would see it that way, like the only source of information is light, and researchers have this habit of being absolutely annoyingly curious. Like, we want to know. We really, really want to know. And all you give us is light, then we better make the absolute best out of that life that we possibly can. And there's a lot of reasons. We got very lucky because light has so much information. Like, I showed you a little bit of a spectrum. I showed you some wiggles that show water. But we understand it so much better. And we also have the opportunity because light encodes the information of where it comes from, where it passes through, what the material is, and so on and so forth. So we are very, very lucky in the sense that we do have light because it carries so much information. Sound, for example, can carry also a lot of information, but light can carry more. So we got lucky there, but again, we're also very annoyingly curious, and we will not shut up until we figure it out.
I know this is an adjacent topic, but we're talking about stuff like Proxima Centauri and that kind of thing. From your perspective, what are the best chances of getting human life to something that far away in terms of light years?
So if you want to get humans there, you would need a multi-generational spaceship. So you would need something that can sustain life for basically indefinitely. Only then can you start the journey. The good thing is, I don't know how people how much you know about relativity, but basically the faster you go, the slower you age. But that doesn't help you fully because even then, it will take generations of humans to get there. So if you want to get there, you need to build a spaceship that can sustain life indefinitely. Not for a long time. I'm going to make this very clear. Indefinitely. And then you can go there, and then you can see, then you're also good, because probably this will not, we say it might be habitable, but that is under certain conditions that we have not yet proven. So it's better you have like a backup plan that you can say.
Within climate, what gets you the most excited? Is it like being able to update the model for a particular climate? Is it the freaking rock clouds, which I still haven't quite processed, or like what else gets you super excited?
Really love the question. Thank you so much. It's basically, imagine like a little kid in front of the television watching a sci-fi movie, and you see all these crazy worlds, like these ice planets that are completely frozen over. If you watch Interstellar, frozen clouds where people walk on it. If you watch Dune, sand planets that have complete like these weird sandstorms and everything. And I think I just got fascinated by that. So I want to really learn what is out there, what kind of environments are out there, and what fascinating complexity do they might hold. Right now, we are I was fortunate enough to be born into a time where we can actually figure that out. I have no idea, maybe if I was born later we might be able to study other things, but right now we are at the verge of really starting to probe this atmosphere from top to bottom. So we start at the top, we start at the gas phase, like what gases are in the atmosphere. We start at the clouds because they hinder our sight. And so this is what personally, again, me gets excited because we're now going slowly deeper and deeper and deeper. And with the models, we can actually push even further. Because that goes back to the light question. We only see a part, like a tiny shimmer of the atmosphere, so we really need the models to go deeper. And I want to know what's below it. I want to know all of it. I want to know all the structures. And that is what fascinates me. On the way there, of course, we improve climate model, we improve our understanding of the universe, and so on and so forth, which I love. But what I really want to know, I'm just curious about that other stuff.
Okay, one more live question, then we have a couple on Twitch.
Really great presentation, by the way. It was really fun. Going back, you mentioned the habitable zone. We need to take it back in school list. Checklists. What are some items that makes a planet, an exoplanet within the habitable zone? Like what classifies it as habitable? And then is weather a factor? Is there certain metrics that it has to hit to make it the climate has to hit to make it habitable?
Yeah, I love this question. Unfortunately, that's a whole 20 minutes talk. So I'll give you the very short answer. Habitable zone is defined as the distance to a planet where water can occur. Just that's it. That's the whole thing. And yes, that very much depends on the weather. Like, for example, one of the reasons why we think Mars is no longer habitable is because of the weather, is because of the atmosphere, as it might have been. Why water? Because it turns out water and carbon are the easiest things to build life from. Not the only, but the easiest. So that's why we're looking for it, just to improve our chances. We know how we can find a planet that might have water, we know which planets don't have, and we know that water helps. So if we want to increase our chances, we've got to look for that. If you want to have more detailed answer, I'm very happy to talk to you afterwards.
Okay, Twitch question. Are those images of weather simulated or real pictures?
Unfortunately, they're all simulated. We do have some picture of real weather, especially if you remember the hot Jupiter. We basically have a fuzzy image of what that looked like from real data. So we are getting close to getting real pictures, but all the stuff that I showed are simulations.
Okay, and the other question I really think you already answered. Yeah, you have. I'm gonna leave it there. And that's it. Thank you so much.